Somewhere out past the edge of our solar system, a machine older than most of the people watching this is still transmitting data back to Earth, and it just handed scientists a puzzle that took nearly 40 years to even begin explaining. This isn't a new spacecraft. This isn't a fresh mission with the latest sensors. This is Voyager, the same probe that flew past Jupiter and Saturn back when disco was still on the radio, and it just forced researchers to rethink something they thought they understood about an entire planet. Stick with me, because by the end of this, you'll understand why scientists are calling this one of the strangest unresolved stories in the solar system, and why the answer only came together decades after the data was collected. And if you want to catch every new discovery the second it breaks, go ahead and hit follow before we get into it. To understand why this mystery is such a big deal, you have to go back to 1977, when NASA launched two nearly identical spacecraft, Voyager 1 and Voyager 2, on what was originally supposed to be a few years of exploring the outer planets. Both were built with instruments that were cutting edge at the time, but by modern standards carry a tiny fraction of the memory and processing power of an average smartphone. Nobody expected them to still be running today. Yet both spacecraft outlived their planned missions by decades, and both eventually did something no human-made object had ever done before. They left the bubble of charged particles and magnetic fields that surrounds our entire solar system, a region called the Heliosphere, and entered true interstellar space. Voyager 1 crossed that boundary back in 2012. Voyager 2 followed in 2018. Since then, these two spacecraft have been humanity's only working instruments actually sitting in the space between stars, radioing back whatever they can sense about an environment nobody has ever directly measured before. Voyager 1 is now so far away that it's about to hit a landmark most people don't even realize is coming. Later this year, in November, it will cross a distance of one full light day from Earth. That means a radio signal traveling at the speed of light, the fastest anything can move according to physics as we understand it, will take a full 24 hours just to reach the spacecraft. And if Voyager 1 sends anything back in response, that reply needs another full day to make it home. So a single question and answer with this spacecraft now takes about 48 hours round trip, before you even account for the time it takes engineers to process the signal or schedule time on NASA's Deep Space Network. Mission engineers have described it plainly. Send a command on a Monday morning and you're waiting until Wednesday morning to see what happened. That's the kind of distance we're talking about. Over 16 billion miles, a number so large it barely means anything until you try to imagine waiting 2 full days just to have a conversation with a machine. But the mystery I actually want to tell you about doesn't come from Voyager 1's incredible distance. It comes from something much older, a piece of data that Voyager 2 collected nearly 40 years ago, and that scientists have only recently figured out how to properly explain. Back in 1986, Voyager 2 became the only spacecraft in history to fly directly past the planet Uranus. To this day, no other mission has ever visited that world up close. Everything humanity directly knows about Uranus from a spacecraft's instruments comes from that single flyby, a narrow window of just a few days where Voyager 2 swept past the planet, its moons, and its strange sideways magnetic field, gathering as much data as it possibly could before continuing on toward Neptune. And buried in that flood of information was something that immediately confused the scientists analyzing it. Voyager 2's instruments detected an electron radiation, built around Uranus, that was far stronger than anything researchers expected. Based on everything known about how planets generate and hold onto radiation belts, Uranus simply should not have been capable of trapping that much high-energy radiation. It didn't fit the models, it didn't match comparisons with other planets. And for nearly 4 decades, nobody had a solid explanation for why those numbers looked the way they did. That kind of unresolved anomaly tends to just sit quietly in the scientific record, acknowledged but unexplained, because there was no way to send another spacecraft back to check. Uranus is roughly 2 billion miles from Earth, and reaching it takes the better part of a decade, even with an efficient trajectory. So for 40 years, this strange spike in radiation stayed exactly what it was, an open question with no obvious way to close it. Then researchers at the Southwest Research Institute decided to take a completely different approach. Instead of waiting for a new mission or trying to squeeze more information out of 40-year-old readings, they went back and compared Voyager 2's Uranus data against something much closer to home, decades of space, weather observations collected around Earth. And what they found points toward a genuinely fascinating explanation. Their analysis suggests that Voyager 2 may have arrived at Uranus during an extremely rare and violent burst of space weather, essentially catching the planet in the middle of a cosmic storm at exactly the wrong, or depending on how you look at it, exactly the right moment. Here's the mechanism researchers believe was at play. The sun constantly releases a stream of charged particles called the solar wind, and that stream isn't uniform. It has faster patches and slower patches, and when a fast-moving region of solar wind catches up to a slower one ahead of it, the two collide and compress, creating what scientists call a co-rotating interaction region. These interaction regions are known to supercharge radiation belts here at Earth. In 2019, one of these events slammed into our planet's magnetic environment and dramatically accelerated the electrons trapped in Earth's radiation belts, injecting a massive amount of extra energy into that region almost instantly. The new research suggests something remarkably similar may have happened at Uranus in 1986, just as Voyager 2 was flying through. If a comparable interaction region swept past Uranus at that exact moment, it could have generated intense high-frequency waves in the planet's magnetic environment, waves powerful enough to accelerate electrons and pump extra energy directly into the radiation belt Voyager 2 was measuring in real time. What makes this genuinely fascinating is that scientists originally assumed the opposite effect was happening. For years, the working theory was that these kinds of high-frequency waves would actually scatter energetic electrons away, causing them to fall out of the radiation belt and into the planet's atmosphere, which should. Both plasma density and the density of neutral, uncharged atoms are expected to keep climbing until the spacecraft reach somewhere in the range of 200 to 250 astronomical units from the Sun, with 1 astronomical unit being the average distance between the Earth and the Sun itself. As of the most recent tracking data, Voyager 1 sits at roughly 172 astronomical units out, and Voyager 2 trails slightly behind at around 143 astronomical units, meaning both spacecraft may still be climbing toward that predicted density peak rather than having already passed it. If that modeling holds up, the mystery isn't really whether the density will eventually level off. It's whether either spacecraft will still be functioning by the time it actually happens. That timing question turns out to matter enormously, because both Voyager spacecraft are running on a strictly finite power supply that cannot be replenished under any circumstances. Each spacecraft carries a radioisotope thermoelectric generator, a device that converts heat from the natural radioactive decay of plutonium into usable electricity. That decay process is physically constant and cannot be slowed, sped up, or reversed, which means each spacecraft loses a small but unavoidable amount of available power every single year, regardless of how carefully engineers manage everything else. To stretch the mission as far as possible, NASA has been forced to make increasingly difficult decisions, shutting down individual heaters, backup systems, and entire scientific instruments one at a time, keeping only whichever systems currently provide the most valuable data per remaining watt of power. Voyager's cosmic ray subsystem was scheduled for shutdown in 2025, with its low-energy, charged particle instruments slated to follow in 2026, part of a carefully sequenced plan designed to keep at least some instruments, and the ability to communicate with Earth at all, running for as long as physically possible. To put the scale of that power constraint into perspective, Voyager 1 currently operates on roughly 23 watts total, an amount of electricity smaller than what a single old-fashioned incandescent light bulb would draw here on Earth. Every instrument still functioning, every heater keeping delicate onboard electronics from freezing solid in the deep cold of interstellar space, and the transmitter sending data back across billions of miles all have to share that same shrinking pool of power. Engineers have already resorted to switching backup heating systems and thrusters that were never intended to serve as the primary systems for this long, simply because doing so trims a few more watts of demand and buys the mission a little more operational time. Every decision at this point is a trade-off, weighing which piece of ongoing science, including the density measurements central to this very mystery, is worth keeping alive at the expense of something else. Despite all of that, engineers have repeatedly managed to extend the mission well past every previous estimate of its realistic lifespan. In late 2023, Voyager 1 experienced a serious communications anomaly that left mission engineers unable to receive coherent, readable data from the spacecraft for several months. A problem eventually traced back to a single corrupted memory chip inside one of Voyager's onboard computers, hardware that had been continuously operating since before most of the engineers now working, the problem had even been born. Rather than accepting the loss, the team worked out a way to reprogram around the damaged section of memory entirely, splitting the affected code into separate pieces and storing them elsewhere within the computer's limited remaining capacity. The fix worked, and by the following spring, Voyager 1 had resumed sending back usable science data from all 4 of its remaining operational instruments, including the plasma wave subsystem still quietly tracking that climbing density trend from more than 15 billion miles away. That resilience matters directly to the density mystery, because every additional year of continued operation gives researchers another chance to catch the right kind of solar event, trigger another usable electron oscillation reading, and add one more data point to a trend line that has now been building for well over a decade without clearly resolving. It's an unusual kind of scientific waiting game, one where the answer to a genuine open question about the structure of our solar system's outer boundary depends less on new technology and more on whether a piece of hardware built in the 1970s can simply keep functioning long enough to see the pattern through to its conclusion. It's worth explaining why this particular question, how density behaves at the true edge of our solar system, matters beyond simple scientific curiosity. The heliosphere isn't just an abstract boundary. It's a genuine physical shield, and Voyager's instruments have already demonstrated that it blocks more than 70% of the cosmic radiation that would otherwise reach the inner solar system from exploding stars elsewhere in the galaxy. Understanding exactly how that shield behaves at its outer edge, whether it maintains a clean, stable boundary, or whether it's constantly compressing and reshaping the material immediately around it, has real implications for how researchers model radiation exposure for any future spacecraft, or eventually any future human mission, attempting to travel beyond the protective bubble our sun provides. A boundary that behaves the way current data suggests, actively compressing nearby material into a slowly building buildup rather than maintaining a fixed, predictable edge, implies a far more dynamic and less predictable transition zone than the relatively simple models many researchers relied on before either Voyager spacecraft actually got out there to check. There's also a broader lesson embedded in this particular mystery that's easy to overlook amid the technical details. Voyager 1 and Voyager 2 remain, to this day, the only two spacecraft that have ever directly sampled interstellar space. Every other measurement, every other model, every theoretical prediction about what that environment ought to look like is built either on indirect observation from safely within our own solar system or on extrapolation from these same two aging data sources. When the Voyager data doesn't match the models, there's no independent third spacecraft sitting out there to settle the disagreement, while researchers are left working with whatever these two increasingly fragile probes happen to send back, sometimes only a handful of usable readings per year, given how rarely the right kind of triggering solar event actually occurs, and building the broader scientific picture one hard-won data point at a time. Voyager 1 is also on the verge of yet another milestone that puts this whole mystery into sharper perspective. NASA now expects the spacecraft to cross one light day from Earth in November of 2026, a distance of roughly 16 billion miles, meaning a radio signal traveling at the speed of light will need a full 24 hours just to make the one-way trip. Suzanne Dodd, the Voyager project manager at NASA's Jet Propulsion Laboratory, has described the practical effect of that milestone in strikingly simple terms, comparing it to saying good morning to the spacecraft on a Monday and not hearing anything back until Wednesday. That kind of communication delay makes the ongoing density mystery even harder to resolve quickly, since every single command, every calibration check, and every request for additional data now has to account for a round-trip measurement in days rather than hours, stretching out an already slow, patient process of scientific detective work even further. NASA currently has no funded mission plan to send a new spacecraft back out to directly resample this same boundary region. Any mission capable of reaching a comparable distance would require a minimum of a decade or more of travel time. Using current propulsion technology, and missions aimed at the outer solar system have historically struggled to compete for funding against projects promising faster, more immediate scientific returns closer to home. For the foreseeable future, Voyager 1 and Voyager 2 remain humanity's only working outposts in that region of space, the only real-time witnesses to whatever is actually happening as our solar system's boundary continues to compress and reshape the material immediately surrounding it. So what does all of this actually add up to? A pair of nearly 50-year-old spacecraft, using a workaround improvised after their original density instrument broke down more than 4 decades ago, have spent over a decade tracking a slow, steady buildup of material at the true edge of our solar system that current models still can't fully explain, following a pattern researchers have taken to comparing, only half-jokingly, to snow accumulating in front of a plow that never quite finishes clearing the road. Whether that buildup eventually peaks and reverses, keeps climbing indefinitely, or reveals something about the structure of our solar system nobody has properly modeled yet, remains a genuinely open question, one that depends entirely on whether two pieces of 1970s hardware can keep functioning long enough for us to find out. It's a strange thing to sit with, the idea that one of the most fundamental unanswered questions about the true edge of our solar system currently hinges not on some future billion-dollar mission, but on whether a corroded chip, a dwindling supply of plutonium, and a decades-old radio transmitter can keep limping along for just a few more years. If stories like this one, grounded in real published research rather than exaggerated headlines, are what you want more of, subscribe to this channel and turn on notifications. Because Voyager is still out there, still transmitting, and there's a real chance the next signal it sends back finally reveals which way this mystery breaks. Thanks for watching, and I'll see you in the next one.